My name's John Hursh. I'm from the University of Florida. I work in the Agricultural and Biological Engineering lab as a chemical engineer. So we're putting bioprocessing perspective on how to utilize algae and related life forms like that to generate various biomaterials from wastewater and waste gas. So, picture of our lab. So, like you guys might have heard, there was a state of emergency issued somewhat recently in Florida about algae blooms. They're not a new thing to the globe necessarily, but in Florida they're a little bit more of a nuisance and from the overabundance of nutrients in our waterways. So the lab was initially founded to try to find a way to anticipate the nutrients going into our waterways and how to mitigate the damage that's done from wastewater that has too many nutrients in it. You'll hear me use this word later, eutrophication. It's basically just too many nutrients that results in algae blooms. So algae as an organism is a protist that's been around for millennia, if not longer. We're not really sure how it originated necessarily, but we do think that it's responsible for a lot of the oxygen that was created on Earth, along with various other kind of kelps and seaweeds and stuff like that. So we want to use that aspect of that organism to treat wastewater and waste gases. Mouse has been a little laggy, but I'll try it. So as you can see over here, these are basically products that you would find from waste gas and waste streams. Specifically, phosphorus is the big player. CO2, which is 97% of Mars's atmosphere, trying to extrapolate that to an extraplanetary perspective. We've found that it does a significant job of removing the CO2, and an important part of that is that most life forms require a nitrogen source, whereas algae can actually synthesize its own nitrogen from nitrogen gas, which is very unusual for life forms. So a lot of the interest in algae is the fact that it creates many, many byproducts as a result of simply existing. So it's kind of hard to read. Left to right, biofuels, personal care products, the list goes on and on. Essentially, there was a lot of interest for algae many years back for being an alternative to fossil fuels. That's kind of the focus on in our lab, but you as well should be very skeptical of people who encourage algae as a biofuel, because it's not necessarily a practical alternative in that it's not monetarily effective economically. It's kind of a poor decision. It makes a similar amount of fossil fuel as is our demand with natural gas and various other energy sources, but it would not be cost effective to pursue. However, when the availability of various chemical sources and compounds are kind of limited, like on a Martian surface, you find that the cost and the availability of those resources is kind of overwhelmed and needs to be balanced with something that can actually thrive and consume what would otherwise not be a very useful resource. So obviously on the other side, you have the nitrates, which is a more oxidized form of the nitrogen, and then breathable air. So this isn't a 100% effective conversion of these waste gases and waste forms of nutrients, but the same way that scrubbers treat pollution to mitigate their damage to the air in kind of a global perspective, it would effectively reduce and provide a local solution to what could be larger problems than that. So think of it as a bioreactor as being kind of a scrubber prior to entering the ultimate conversion of, where you're putting your wastewater and your waste gases. And it's kind of a precursor that would provide you with materials that you wouldn't be able to find otherwise on the Martian surface. So the value in performing the experiment of the title of my presentation, which is basically converting polysaccharides into sugars. There's very low energy required in the maintenance of it. The pre-existing systems, like I mentioned earlier, for the treatment of your air and wastewater, it would precede that and result in less of a demand being put on the other systems. The phosphorus that I mentioned earlier is an essential resource as far as gardening and horticulture perspectives are concerned, and we can, with 98% efficiency, remove the phosphorus from the wastewater streams and put them in sort of a packaging layer that you can use as fertilizer. So that's kind of an extra benefit of being able to remove all of the waste contents. The complex carbohydrates and proteins that I mentioned earlier, we can genetically modify these organisms also to create specific proteins and sugars and carbohydrates that, you can essentially make the recipe in the DNA for what you're looking to extract from your system. And this is all being grown with stuff that is normally a problem, especially if you're applying it to a Mars perspective. So the value that I've been able to derive from the Mars aspect is that if you're trying to transport an energy source from Earth to Mars, you have to get it off the planet, and adding extra weight to your payload is not a very effective way to do that. So in the first 2 bullet points, we see that methane, which is another byproduct that you can get from composting, or not composting, but digesting the algae. So the biomass, then the byproducts, and then the CO2 and the nitrates that are emitted that way. The biomass you can actually convert into methane through digestion, and I'm not really going to get into that, but that is a valuable resource that I use as kind of a metric to compare the energy density of methane and ethanol. So with methane, we see a higher inner density per mass, and ultimately is more valuable if you're trying to transport fuel off of Earth. So when you get to Mars, what you care more about is the volume of it. So this is why I've pursued trying to derive ethanol from the sugars that we create with the algae. So essentially, you have these polysaccharides, and you want to break them down into usable sugars, because the sugars aren't immediately available for conversion into ethanol when they're grown in the media. So my hypothesis was that to get the most glucose to convert into ethanol, I imagined that we would need the most EPS we could. That's actually a picture. Sorry, EPS is extracellular polysaccharide, but that's kind of a gross word. So the most EPS that you can produce, a certain acidic concentration in addition to heat would actually decompose the polysaccharides the most. So that was my idea. This is my setup. It's about 3 liters of media with 4 liters of air per minute, and then the array of 12 LED lamps at the bottom of the unit. And then the media contents were phosphorus, trace minerals, magnesium, etc., carbonate to increase the pH of the system, but also salt, because the algae does work in a saline environment so that it doesn't compete with fresh water. So don't necessarily need to read into the flow process there. I just wanted to indicate that I did make an error in the experiment, in that when I tried to separate the EPS from the media, I extracted additional biomass in addition to the polysaccharides, which basically means that when it comes to converting the polysaccharides into sugars, I'm going to see a lower conversion rate simply because there's biomass that isn't readily available to decompose into glucose. So this is a picture. The top one is before, when it was still relatively wet after the extraction process. Below is dried. I crushed it up. What you see on the right is a desiccator. So there are a lot of salts in the bottom that absorb moisture out of the air. And in doing that, they remove moisture from the polysaccharides. So we dried it up and crushed it up, and then we were ready to test it for glucose. So in doing that, you use the DNS method, which essentially is a site-specific acid that oxidizes your sugars. No, it reduces your sugars. And based on the extent of the oxidation, it will change color. So you use an amount of sugar, you use known samples that have known concentrations of sugar in them, and then you put them in a spectrometer. And so then on the right, you can see that you graph the spectrometer readings, and there's a linear relationship between the optical density of the sample and the sugar concentration. So I'll use that for my actual samples. So after we've done the calibration, I put the same amount of the EPS in each one of these sample vials. And then after the various incubation methods, we receive the final product. So these are the results of what I found. So initially I expected acidic environment, heat, to contribute to the breakdown of the polysaccharides. One thing I did neglect to mention is that we included enzymes because they're not going to break down on their own. They do need the enzymes to have that happen. So I did a control group. I can't really move from the mic. So far left is the control group, and then these two columns over here are basically the enzymes without any acidic treatment, no heat treatment. Then here we have heat treatment and enzymes, and then acid, heat, and enzymes. So that way we would be able to figure out, which combination of all of these does the most for reducing the polysaccharides into sugars. So we found that actually I was incorrect in my hypothesis, and that the most effective method was simply heat and enzymes, no acid needed, which is a surprise and also way more effective because you don't need an additional material to do your breakdown process. So just kind of a larger perspective on how that experiment was conducted. We separated the EPS, dried it, did a preliminary phase to calibrate the sugars. We separated them into separate vials so that we could assess each breakdown independently of each other. And then we did quantitative analysis prior or afterward. One thing that I had not done prior to this presentation is actually convert the sugars into ethanol, because the sugars that I created were broken down in the quantitative analysis process. So that's something to be done at a later date, but we do expect 60% of your sugars to be lost in the process. So in the corn industry, corn is the primary starch that we use to convert into ethanol, there's about a 40% efficiency in mass of cornstarch that is converted into ethanol mass. So just for some context on the two industries. So I took an acre of corn and an acre of algae, assuming that the algae depth is approximately 30 centimeters because there is some light penetration issues associated with anything being deeper than that. I found that you get 775 liters of ethanol a year. For the same amount of land, you actually get 4 harvests of ethanol, simply because corn requires a year to grow. Ethanol, or the algae requires less than 3 months. So with some time for, re-adding your algae, and then the labor time associated with that. So I actually found that it's about 50% as effective as corn, which from an earthly perspective is not that great. It's actually pretty terrible because of all of the work that would have to go into the removal of the EPS, the separation, and then the application to converting it into ethanol. However, no one's going to be able to grow corn on Mars to the same extent that we can grow ethanol, simply because corn requires an obscene amount of variety of variables, and the algae is actually a fairly simple thing to grow, and it fits whatever unit you put it into and whatever crazy space allocation is required in the habitation unit. And so that's my presentation. Do you guys have any questions? Yeah.
Yeah, when you were making the energy density comparisons with methane,
Right.
assuming
That's compressed methane.
yeah, so you
Assuming liquid methane or just high
It's
pressure?
compressed to 120 atmospheres was the figure that I got. I don't know if methane's liquid or solid at that.
Okay. Yeah, I mean, it would just be interesting to include the energy required to either compress or cool to cryogenic.
Right.
In your energy comparison to be more favorable for ethanol, which is liquid at room temperature. It's a lot easier to deal with.
That is a good point. I didn't consider that. Another question?
Did you happen to simulate Martian soil or get someone to help you with that and try to grow the algae in that soil?
And so, algae requires liquid media.
Yeah, right, which is fine. And you can put that in a warmed up dome and throw it in the dirt on Mars. Did you think about possibly trying that? There are simulated soils, Martian soils being worked on.
Are
Here.
you interested in the application of the soil to the liquid media?
I'm interested in, can we take algae, whatever species you're working with,
Right.
and take it to Mars and just grow it?
Absolutely not. It does require a liquid media because it is a.
Yes, I understand that. If you warm the soil, which is 2% water,
Okay.
frozen,
Okay.
make a dome,
Okay.
can you throw the algae out in the soil?
We
And there
haven't
is water?
considered that at all. No.
Okay, just a question.
Okay.
Speak up.
There are components in the Martian soil that is not able to grow either algae or conventional vegetation.
Okay, because there have been experiments.
Yeah, there has been.
And what, can you just explain to me what's keeping that from happening?
It's a compound. I think it's some kind of salt that there is in the Martian soil that I believe so.
I was going to say perchlorate.
Actually, there's a team of Puerto Rican people trying to develop on that problem, but it has not been conclusive yet. So.
There are experiments then.
Yeah, sure, but yeah.
Do we have any other questions? Okay. Thank you very much.